Mohammad Hussein. I am the instructor or the coordinator of this course. Welcome to Changing the World with Chips. So many of you are here to know about what are the chips, what are the semiconductors. And along with you, there are many more. They are being connected via online. Okay, and welcome to them also. So let me show you something first to start with. So which basically that what are the things that we do today with the electronics? Obviously, you have the smartphone, and obviously, like that if you are thinking about the self-driven car, or like the robotics, you have a Segway or something like that. They all have electronics, but at the heart of the electronics, they are essentially the semiconductor chips. And what are semiconductors? So semiconductors are materials. Through that, we can control the current. Sometimes, the control is more difficult. Sometimes it's much easier. And semiconductor ecosystem today in USA employs more than 275,000 talents. And what we understand today that we are going to need more than 50,000 of you. And that's why we are introducing from Purdue University this course to introduce to our youth, to the next generation, the impact and the meaning of semiconductors, okay? And to do so, we have partnered with 15 different companies today. And our first speaker is someone who is the Chief Technology Officer of Skywater Technologies, and he is Steve. Steve actually graduated. He got his bachelor's from University of Minnesota, and then he received his PhD from University of Arizona. His hobby is golf, and obviously he has a life philosophy that he will be talking about during his talk. But more importantly today, that he is going to talk about something which is very critical to the West Lafayette community and as well as the state of Indiana. Steve's company is one of the trusted companies for the US government today to build semiconductor chips in the USA, Skywater Technologies. Their main office is in Minnesota. They also have another fab or the foundry, which is in the state of Florida, and they have announced their next one is going to be in West Lafayette. So a round of applause for that. So, having said that, he is going to talk about 25 minutes or so. Then we have collected many questions from you, and thank you for that. And from those questions, I have picked 7 questions. Those are the questions which have come from you many times, and that's why it's the median value. And then I will be taking 3 questions from the audience. Okay? So it will be 50 minutes in general, and from that, Steve, the mic is yours.
All right, thank you. Can you hear me okay? Yeah. All right, so thanks for that tremendous introduction. Thank you for attending the class today. Like Professor said, my name is Steve Kosier, and I am the Chief Technology Officer at Skywater Technology. And it's my great pleasure to be here to get to explain to you a little bit about semiconductors. I'm assuming maybe you don't know much about semiconductors, you're interested, you've heard about it. We're going to try and go through some of that today and get you an overview of the industry and explain why it might be interesting for you to pursue a career in semiconductors. So before doing that, just a little bit about me, just so you know where I'm coming from. I'm the Chief Technology Officer at Skywater Technology, and I got my bachelor's degree at University of Minnesota, PhD at University of Arizona, all in electrical engineering, so I'm an electrical engineer. And I worked at Polar Semiconductor for many years, doing lots of process development work, all sorts of technologies, power management type of things. I was president of a startup company, Canamax, for 3 years, and now I'm at Skywater as Chief Technology Officer. I'm also an adjunct professor at Vanderbilt. And so pleased to be here. If you want to know more about me, of course, you can check out my LinkedIn profile. So let's talk about semiconductors. So what is a semiconductor? So semiconductors are an important part of all our modern lives. They're an essential component in all electronic systems, and anything with an on-off switch has a semiconductor in it, and many have many semiconductors in it. So the picture on the right is some wafers with ICs. ICs are integrated circuits, and the round things are the wafers, and they're sliced up, and those rectangles are the chips that are made on the wafers. And so a question to ask yourself, you've all written code. I know you have. You wouldn't be an engineering sort of student if you hadn't written code. Where do you think your code goes to get executed? Well, it goes to some semiconductor processor and memory units somewhere that's actually doing all the execution. So something you're familiar with is your smartphone. Everyone has one. So if you look inside a smartphone, here's an Apple iPhone. You're familiar with the way it looks on the left, the front and the back of your phone. But now take the screen off and look inside a minute, and you see there's a lot of dense assembly and a lot of tightly packed and carefully crafted components. And then if you take that off even further and look more deeply at the boards that are in there, what you'll find is that they're packed with chips like those rectangles on the previous slide made on wafers. And all these chips, they come from all sorts of different companies, okay? And they were all designed to fit together in just a certain way. And there's software running on this, and the software and hardware all have to work together. And of course, it has to fit the form factor and all sorts of other things. So it's a tremendous engineering achievement, the smartphone. But it illustrates kind of how complex the supply chain is for semiconductors. So that's what this slide is about, the semiconductor value chain. So value chain starts on the left with materials, just basic materials. And there's many companies, and you can see all their logos listed there. But from materials and tools like capital equipment that you actually use to process wafers, you move from there to IP and design, fabrication, assembly and test, subsystems, systems, and finally end markets. And all the way, for example, Comcast, Charter, AT&T, these are communication service providers that you and I actually exchange money with. All along the way, though, it's all these kind of business-to-business interactions where all these companies are working together to add value in their little slice of the chain. Now, the course that you are going to have here has 15 speakers, all from different places along the continuum here. Skywater is a foundry, so you can see the Skywater logo at the bottom under the foundry, with Global Foundries and Intel, Samsung, TSMC. Also an OSAT, which is assembly and test. So Skywater plays in that piece of the value chain. So that's where we'll talk about in a minute. And so the thing about the semiconductor industry is, and the world has sort of woken up to this recently, is it's a vital piece of many industries. Automotive industry for sure, smartphones, computers, communications, aerospace and defense, healthcare, everything relies on semiconductors. And the COVID-19 epidemic underscored this importance and brought it to the forefront of everyone's minds. And the semiconductor content in all sorts of goods is increasing and continues to increase and has increased for decades and will continue to do so. So it's an important industry, it's a big industry, and it's growing. So this is a good place for you to be focused on as you look to your future. So semiconductors and silicon in particular is quite interesting in that the material that we're using to build these things is really something everyone knows very well. It's sand, like sand on a beach. This is melted and formed into a crystal. It's called a boule. That's that cylindrical thing to make high quality single crystal silicon, which is very high purity, and that is sliced up like so, into wafers, and it's the wafers on which you produce the ICs, the circuits. And so Skywater, you can see the logo down there, Skywater is in that kind of business, processing wafers. So this involves repeatedly exposing a pattern, etching away, depositing, and this kind of thing to make the structure. And then once done, then the wafer gets diced up into a package and into a board. And so, you know, that's part of the value chain that we saw on the previous slide. And you know, one of the important things about semiconductors that you should understand is just how small the dimensions are. So down below, there's a couple of cross sections you can see. These are interconnect lines that were made at Skywater. And the dimension, you know, 100 nanometer, 43 nanometer, these are the kind of dimensions that are typical of semiconductor processing. And in fact, leading edge semiconductors are much smaller than that even. And this is just really small and kind of hard to even understand how small it really is. So just to kind of put it in perspective, you know, a tennis ball you can hold in your hand, an ant is about 5 million nanometers. Human hair width is about 100,000 nanometers. A red blood cell, 10,000 nanometers. So the dimensions we're talking about when you talk about ICs are tens of nanometers. So somewhere between DNA and red blood cells. This is the kind of features we're printing on these wafers to make these devices that we all use today. Skywater goes down to about 45 nanometers. The most advanced, you know, wafer fabs do something all the way down to 3 nanometers, getting close to like DNA size. The cost of doing this grows exponentially as you get smaller, but the performance improves, so people keep doing it and will continue to do so. So, you know, that's kind of what the semiconductor industry is. It's a very big industry. It's very complex. There's a lot of pieces to it and a lot of companies that interact along the way, you know, to deliver something in the end that you or I would buy, you know, as a consumer. So a little bit about Skywater. So Skywater is all about streamlining a concept to production journey. So one of the results, or one of the implications of having it be so expensive to process wafers is that it's very, very hard to try new things. And so if it's hard to try new things, it's hard to innovate. Skywater tries to fill that gap and streamline the concept to production journey, which is really a focus for our national security right now with the CHIPS and Science Act. We are a US-owned pure play foundry, and we used to be the only one. Now there's another one. We're still, you know, the biggest one. But you know, we do all sorts of technology development aimed at, you know, streamlining that journey from concept to production. We have sites in Bloomington, Minnesota, which is on the left, and also in Florida in the Orlando area. And as mentioned, we're planning to build right here in West Lafayette. So you know, there's a timeline there, and we're expanding, you know, our operation as we go. So a lot of trusted processing. We do a lot of work for the government, and but the main focus is to address the so-called Valley of Death. So maybe you've heard of the Valley of Death, but you know, technology as a service is our business model, and so what that means is that we do the innovation, the development work, and the manufacturing in the same facility, on the same equipment, with the same, you know, people, which the reason you do that is to bridge this Valley of Death. The Valley of Death is this space here between the government lab, which you see on the left, and the corporate, you know, development or manufacturing, which you see on the right. And the axis is the technology readiness level. So on the, you know, on the far left, you've got, call it basic research. On the far right, you've got full production. And somewhere in between, you know, there's research and then there's production. But how do you get from production, you know, how do you get from research into production? Not so easy to do, but that's what we do at Skywater. That's what technology as a service is combining those two things and making it frictionless to move into production. It's a really big problem, and it's a really important issue for the country to be able to innovate well and efficiently and quickly and get it into production so it's impacting the lives of people quickly. And so that's where Skywater's focused. You know, the other thing about Skywater is we talk about a lot of long tail opportunities. So when you hear someone talk about the long tail, they're referring to some kind of, you know, Pareto chart like this. So this is a picture of production volume versus number of chip designs. And so, you know, on the left, where the volume is the highest, this is where you see the big volume driving products like smartphones and PCs. These drive huge volumes of chips, and these are the things that you build factories to run. And you're running one of them, and that's what runs. So it's very much, you know, kind of a all or nothing kind of thing. But then there's this long tail of low millions of products that exist, and these are things that serve specific small niches that are not being served by the applications that are driving the big volume. But this is where innovation happens, and this is where opportunity exists to do disruptive things that then can come to volume and take off. And this is where Skywater focuses. So examples might be Internet of Things, you know, everything's got some little sensor in it. Edge computing, you know, doing more computing, you know, locally, not always communicating with satellites. Highly customized chips that do specialized things at low volume, sensors, this kind of thing. So Skywater does a lot of that kind of work, and you know, and so we end up serving a whole lot of applications. Some of them are listed here, and some of the platforms are shown in the rows, and some of the applications are, you know, in the you know, pictures, like power conversion, transceivers, imaging, battery management. So the interesting thing is that the chips, you know, semiconductors can serve every market in all sorts of applications in ways that you might not imagine at first, but if you can invent a way to make it work, then it can be very powerful, because once you have it working in a semiconductor factory, you can really produce a lot of product quickly and efficiently and go to ramp very quickly. So anyway, that's about Skywater. And one of the things I wanted to talk about, especially to you all, is about semiconductor careers. So Skywater has lots of open positions, lots of similar companies do as well. We need lots of engineers. We need design engineers, device engineers, process engineers, yield, facilities, industrial, quality, reliability, metrology test, you know, mathematicians, statisticians. There's just a need for all of the above, and the reason is that it's such a it's an industry where the factory itself is complex, and there's like subject matter experts needed at each little step, but there's also the whole that has to get put together both within the company and then looking up and down the value chain to keep all that together and keep it you know, abreast of all the trends. It's just a very fast-paced, challenging industry to be in, and very exciting. You know, my personal anecdote there is that I was in the semiconductor business for 20 years and then left to be the president of a startup company, which was great, but it wasn't in the semiconductor business. And I can tell you that the pace just was so much slower, and I missed it so much. I was so excited to get back in. So once you're in and get a taste of how fast it can go, it's a really fun thing. And there's a lot of growth opportunities. We have lots of, you know, we hire lots of college grads, bachelors, PhDs, lots of these degrees, like I'm saying. So, you know, we can talk later if you want to know more about it. We have internship programs. We have lots of them in Minnesota and in Florida. We'll have even more, you know, this summer. Anyway, that's a very brief overview of what the semiconductor industry is and how Skywater fits in it, and you know, why you might think this is a good thing for you to pursue. And here's a few details, about me. Again, you can find me on LinkedIn and so on. So anyway, that's what I had to present to you today, but I'm eager to hear the questions and have a discussion.
Thank you, Steve.
Yeah.
Great. So I would like to thank you all because all of you have submitted some questions. And the number of questions is actually humongous. And I must say thank to Zach, our TA, and the whole team of TAs, because they're ciphering through all these questions and then chose 7 of them. And I'm going to actually ask you those questions.
Good.
So my first question is going to be about, from the class, is about the technology as a service model, okay? Mm-hmm. So in this one, how does the model benefit the company and the customers? So that's number 1.
Yep.
And then B, is this something recent, or has Skywater always liked this, something like this model? And how is it more efficient, and how does it benefit product development?
Yeah, great questions. Right, so technology as a service, this is something that Skywater has been about since Skywater was founded and formed in 2017. So the legacy of the site, the wafer fab was owned by Cypress, which was then purchased by Infineon, and it ran just as basically a factory, a CMOS factory for decades. And in 2017 is when the ownership changed and became a pure play foundry, opening up to all sorts of customers and with a new business model. So the new model is technology as a service. What it means is, wanting to attract all sorts of customers. So anybody that has an idea and has money, and it aligns to what we think, our capabilities are, where there's a match, then we engage in a project that's very focused, it's very collaborative, and the advantage to Skywater's customer of this model is that they understand that they're going to be able to develop something that's new and unique in the world, and that they're going to be able to manufacture it when it's done readily and easily and quickly. Because the alternative is to develop something new at a research facility or a lab somewhere, and then try and find some place to transfer it to manufacture it. And that's very expensive and takes a very long time. And the fact is that if you do that, chances are you're going to spend a lot of money and actually miss your market window, and it won't result in business success. So that's the benefit to the customer.
Great. My next question on behalf of the class is, how do you determine what projects are a good fit for your company, and how do you help the project leads advance their research?
Yeah. So, so there's criteria that we have for which projects we accept. We talk to lots of customers and work with them closely to define something that, well, first of all, the first filter is are we capable of it? And if the answer is no, then that's easy. The second filter might be, are they serious about moving to production? Or is it just kind of a research project? If it's a research project, it's probably not the best fit for us because we want to run production. The next filter might be, of course, there's business terms, but what we have to do is take their idea and turn it into something that can actually be executed in the factory, and figure out what it's actually going to take to run that whole project and make it work. But then there's a business discussion about, can you afford it, and does it make sense for us both? So it's that kind of process.
Yeah, always a balancing act.
Yeah, right.
Okay, my third question is, the Skywater's website mentions a post-Moore's law reality. And how do three-dimensional transistors change the market for semiconductors? And what are some steps Skywater has taken to maintain competitiveness in this new market?
Good questions.
Very
So
matured question, by the way.
I'm glad you checked the website.
No, that's actually part of the, the pre-class assignment.
Yeah? So if I have a pop quiz or something and call on someone, they could answer some questions?
I'm sure.
Yeah? All right. So anyway, those are great questions. There's a couple important statistics and things that should be noted about leading edge semiconductors, trailing edge, Moore's law, post Moore's law. So Moore's law refers to basically the doubling of transistor count every 3 years or so. It's basically an exponential increase in density, and so enabled by smaller and smaller and smaller features that you're able to print on a piece of silicon, and those do bring performance gains, and those are especially important for microprocessors and for memory, which are at the heart of systems such as your smartphone, and those so keeping up with that and continuing to push that trend is extraordinarily expensive, right? So today to build a leading edge factory to make chips like that is you're talking about, I don't know, $15 billion or so, and that's billion dollars, right? That's an enormous amount of money. There's not that many companies that have that much money, and so when you spend that much money, you have to very much focus on things that can fill that factory and get your money back when you run, and so what that drives is a need to focus on things that you know are going to be there and are not going to try and, you're not going to go off in some crazy direction. You need to stay on the path. So you end up with kind of this self-reinforcing system that when you're chasing Moore's law, it means you're investing more and more dollars to make denser and denser chips to serve these markets. But the thing that doesn't get as much press is actually most of the semiconductors produced in the world are at the so-called trailing edge nodes of 90 nanometers, 130 nanometers, 180 nanometers. So like most of the silicon actually is in those nodes, not in the super advanced nodes, and those trailing nodes are growing just as fast, if not faster. And the reason is these are the nodes where you see a lot of consumption by the automotive industry, the power, anything to do with power management, anything to do with green energy, anything to do with like microelectronic MEMS, micromechanical systems that move and oscillate, anything to do with photonics, where you're doing waveguides in silicon, guiding light, and doing interference patterns and so on, or a lot of the bio stuff. All of those things don't need the super small and super expensive, lithography that is required to do the leading edge processors. So that's where Skywater focuses. So it's, so we're not, focused on what we can't do because of our lithography. We're thinking about all the things we can do because of all the innovative ways we can apply what we have to these kind of new applications. So that's kind of the way Skywater approaches the question. Yeah.
Right. I think that's a great information, because it really shows that many of you at some point 3 years or 4 years from today would like to be entrepreneur, right? Would like to have your startup. And then rather than going to TSMC or Intel, which are big foundries, right, or the fabs, you would like to have someone who can actually help you to be in the rocket, and then you go up front. Okay, so my next question is how has Skywater adapted to struggles like silicon shortages and supply chain disruptions in your rapid process?
Yeah, yeah. So supply chain shortages affect everyone. They affect us as well. Some of the more important or significant ones for us tended to be some of the process gases last year. Things you wouldn't maybe think of, like nitrogen and argon, and these things, they'll come from different parts of the world, actually, that sometimes there's conflict, and their supply is not easy to get. In the case of Skywater, because we serve a lot of important government-related projects, there's some help there in getting the supply, but it's a big challenge, and it's certainly an issue for the industry. And as you look at kind of this picture, so it's kind of an eye chart. There's so many logos on there, but one thing that I want people to understand is that there's names of companies on here from all over the world, right? A lot of the OEMs and the EMS people, PCBs, a lot of these folks are in Asia, and so yeah, we can have our differences, but all these people, all these companies have to interact to get something finally to the end customer. And so, so when you look at a picture like this, it's maybe easier to understand why there could be a supply chain disruption, because in fact, it's kind of more amazing that it works. It's kind of amazing there hasn't been more, actually. It's a challenge. I don't know. I mean, you just have to work through it. It's one of these things where you manage your suppliers and you hope to partner with them and work through it.
Great. So there is something that Skywater is the only company in the US specializing in the production of chips. What is the main reason for the low number or small number of companies in this sector in the US? Is this phenomenon purely strategic or more related to a low amount of knowledge in the country on chip productions and semiconductors?
Well, okay, so we're certainly Skywater is not the only company in the country producing chips. But we are one of the only U.S.-owned pure-play foundries. So the distinction there is, like on this chart, you see the integrated device manufacturer, IDM. So these are companies like Intel, Texas Instruments, NXP. So these are companies that span quite a few of these pieces of the value chain. And so Intel, for example, they design chips and they also manufacture them and they also package them. So they're called an IDM. So they certainly know very well how to manufacture wafers. But what has happened over the past 20 years is there's been a shift in the industry, and it's called the fabless foundry model. And what it means is that foundries formed that focus on just chip manufacture, just wafer manufacture, the business of manufacturing wafers, and let the design houses focus on designing chips. So they're fabless, so-called fabless foundry model. So it used to be the opposite of that, or an IDM would have both, but a fabless foundry model is splitting those things into two. And so the foundry growth has been in Asia, and in Taiwan in particular, but China also, and Korea. And so why would that happen? Well, the fact is that it's really hard and it's very expensive to manufacture wafers. And so when governments get involved and subsidize that, and they offer their service, and they do it very, very well, and it's very inexpensive, and everything's working, it's great. And it's the thing is, the problem is, it's great right up until it isn't, and right up until you can't get what you want. And that's why you see the emphasis on reshoring and bringing some of this production back to the U.S. to make sure we're not, beholden to that. But all of this stuff, all of the things that are being that grew up and were manufactured in Asia, they all started in the U.S. It's certainly not because we don't know how to do it. It's simply a business decision that says it's cheaper to get it made over there, and why not? What's the reason not to have it done that way? And it's sound logic, dollars and cents wise, but not when you can't get what you need, one. And the other piece is that, if you're not actually manufacturing the thing that you depend on, you don't really learn how to advance it the next node and the next generation. And that's often the key that makes your product successful. So I think there's a growing realization that it needs to come back to the US, which I'm very thankful for.
Yeah, and I think the next question is actually going to relate to that. But what are the skills that you think are important for the evolving semiconductor industry?
Well, skills. So, the skills, generally, the skills that you're always looking for are people that are agile and kind of, I'll say, technically aggressive, that are willing to go learn new things and try new things and, make something happen. And, in the case of, the semiconductor industry in particular, there's a whole lot of science and physics and stuff behind it, energy bands and equations and so on. But it's also a really, really big business, and a lot of money changing hands, a lot of money to be made, a lot of big bets to be placed, and there's a lot of room for all that. So I think people that can, work on the technical and also kind of deal with the fuzzy and soft, interplay of the reality of getting things to finally get done. These are the skills that will always be successful, right?
Yep. Great suggestion and advice. So from the class, that the seventh and the last one, and then I will go for the live questions. So that there is a lot of emphasis definitely on the smaller nodes, and compared to that, the Skywater processes are 90 nanometer node or in the same vicinity. Mm-hmm. So what do you think, what are the challenges with that size of the node? And how do you interpret that the society is advancing, in a sense, that more and more in context of the smaller nodes? That's where there is a definite, the affiliation.
Yeah. So, well, again, so smaller nodes, so smaller feature sizes make denser circuits, and denser circuits make faster and more powerful logic processors. So if what you're trying to do is make faster microprocessors, you need smaller nodes, no question. But that's not the only thing that needs to be done. There's lots of other things needing to be done that don't depend on that at all. Again, a lot of the projects we work on these days involve kind of biomedical work where there's microfluidics, where there's samples going through microchannels and getting analyzed, or there's solution being put on top of a transistor and you measure its threshold voltage change, or you might have other things like quantum computing, where you've got superconducting interconnects and elements like that that are behaving in strange ways when you lower the temperature. So all of these things are important, or things like managing power, like turning high voltage into low voltage, turning the AC outlet into something that can power your device, and doing it efficiently. It's all important for saving the planet. None of that actually requires really fine feature sizes and really small nodes. What it does require is using that which you have in new and different ways that match up with the application requirements. So it's a different way of thinking about it.
Right.
Yeah.
Great. So I will be actually, so I did a count when I was studying here, 60, 60, 60, pretty much. So I'm going to first, from here, whoever raises the hand first, I'll be taking one questions. It's kind of like a rapid fire round. Okay. Whoever would like to ask a question, please go ahead. Otherwise, I will steal that slot.
Somebody must have a question.
Okay, one of the questions on behalf of your side, you have a life philosophy, and why is that?
My life philosophy, that's right. That was one of the questions you asked me, what's your life philosophy? So I thought about that for a while, and my one-sentence life philosophy was that the whole is more than the sum of its parts. And what that means, you can apply it to a lot of situations, but I mean, for you as students, right, it's, you're going to be some, electrical, mechanical engineer, or whatever it is you're going to choose to do. So that's one thing you are, but you're that and something else, right? That you're in the, the soccer club, and you're a golfer, and you're doing some journalism thing, and something else, right? It's the and that you tack on to what you're doing that becomes more powerful than just the single thing, right? So it's important to always think about, I'm doing this, I've learned that, and I know this, and I think I could do that. Maybe I can put those together and move in that direction. So it's kind of like realizing that, that when you do that, when you combine stuff like that together, it's more than just those two things alone. It's something more. And that's special, and you should always do that. That's my life philosophy.
Thanks. Okay, from this side. Yeah, please, go ahead.
This is going to be a tough question, but what's your hand?
Introduce yourself first.
My name is Kaiza E. I'm a freshman here at Purdue University. My question is, what is your handicap in golf?
Well, my handicap, that's, all right. So I used to be single digit, but I'm not anymore. I would say 12.
Okay,
Yeah.
great. Okay, so from the middle one, yeah, please. You need the mic, I guess. Oh, very good. Go ahead.
All right. So I know you plan to build a facility in West Lafayette. I was wondering if there's a specific new capability you're hoping it'll add to Skywater, or if it's simply expanding your current capability.
Oh, yeah, good question. So the question's about the facility in West Lafayette. Will it expand capability, or will it, what will it add? How does it fit? So, right, so the two facilities that Skywater has are both 200 millimeter facilities, meaning that the wafers we process are, 8-inch diameters. So in West Lafayette, it'll be 300 millimeter, 12-inch diameter, so bigger, right? This big, like a small pizza kind of size. So that's one, that's an important difference. And another is that the feature size, we're talking about feature size. The feature sizes will be smaller at this facility. So it extends the capability that Skywater has to serve the various customers that want the smaller feature. And usually, and the way it's worked in the industry is that the smaller feature goes hand in hand with the bigger wafer. The transition was made, you know, a couple decades ago, actually. The industry just moved to the larger wafer size. At the same time, the feature sizes shrunk. So to kind of get the next smallest features for Skywater, we really need to go to the higher wafer size. So that's, yeah, so it definitely adds something to Skywater, you know, production capability that we don't have right now. Yeah.
Yeah, thank you so much, Steve. This was our first session, and thank you so everyone for being here. And obviously, another round of applause for our speaker. So to wrap up things, in Purdue, we do have for you to start with, this is the introduction to semiconductor. And then there is this summer opportunity, which is called the STARS, summer training on awareness and readiness for semiconductors, to make you specifically skilled for semiconductor-related job opportunities, especially internship and so on and so forth. And then you have the vertically integrated project that actually to continue and to apply your skills. And then you also start taking courses, which is the concentration, and then you receive your degrees. Okay? So I look forward to seeing you in next week. Thank you.